Hello, Physics 1. Welcome to part 1 of Monday's lecture for week 14. This is your last lecture leading up to the exam. It will go through all of section 8.2 in the various parts. So you know that your exam will not go further than 8.2. All right, so we get to do some really fun stuff in this chapter. This whole class has been a riot, so it's just more fun. So one of the most exciting discoveries of the last century is that energy levels within an atom are quantized and discrete. That means that electrons that are bound to atoms are only allowed to exist at particular energies. Atoms can only have particular energies. And they can never be in between. They're either all in or all out. So no in-betweens. So you can think of it like you've got these energy steps. You're either on this step or this step or this step. You're never in between two steps. That's not allowed. So in the classical view of physics, you would have this smooth transition. So this is classical, and this is modern, and also accurate. All right, so this is the idea that I want you to keep in mind as we go through the rest of chapter 8. And we're really just going to be introducing and laying the groundwork for how to think about quantized energy levels within atoms. So, going back to our energy principle, in terms of energy, this means that only certain values of K plus U are allowed if the electron is bound. Okay, so let's draw an energy level diagram. Illustrate this further. And we're really building off of something that we introduced in chapter 6. So on the x-axis we have R, which is the distance from the proton. So in this case, what we're going to be looking at is the hydrogen atom, although the same structure exists for all atoms. Okay, so what you would have is you'd have this curve that would look like this. And then you'd have these allowed energy levels. So E1, E2, I'm not drawing this to scale, E3, E4, etc. And so these are the allowed states. If it's not in one of these energy states, it is not allowed. And these are quantized. So for the hydrogen atom, En, the energy level, is equal to K plus U electric, which is equal to minus 13.6 eV over N squared, where N is the corresponding energy level. So that means that for E equals 1, you would have minus 13.6 EV over 1 squared, which is equal to minus 13.6 eV. This is the lowest allowed energy for the hydrogen atom, and each particular element will have its own set of energy levels. And no other states have ever been observed. These are the only allowed ones. They must follow this structure. All right, so moving on. Now, if the electron is free of an atom, unbound states are not quantized. It can have whatever it wants in terms of energy. And then you can think about that more in terms of a classical sense. So in this case, K plus U is greater than or equal to 0. If it's less than 0, it's bound. It is with the atom and has only allowed states. So the electric potential energy of a bound electron, so a bound electron to a proton, which would be in the nucleus, is always negative for all separations. And we can see this by just going back to our electric potential energy formula that we've seen prior. So U electric is just 1 over 4 pi epsilon naught Q1 Q2 over R, which is the distance between them. So for an electron bound to a proton, we have 1 over 4 pi epsilon naught plus E for the proton minus E for the electron divided by R. And then we see this is just 1 minus 1 over 4 pi epsilon naught times E squared over R. Since you always have a plus and a minus, that means you always have a negative electric potential for the bound electrons. So this is, if you're wondering why this is, we can just see this just by going back to our standard electron potential energy formula. So just a note, so rigorous treatment of understanding these energy levels comes from studying quantum mechanics. So we're just really introducing quantum mechanic concepts in this class. However, if you want to see a more thorough introduction, take Physics 3 or modern physics. And we will introduce the Schrodinger equation, open to anyone who has taken Calculus 2 or higher. And I highly encourage you to take that class. It's going to be offered next spring. Very excited about it. All right, so moving on, looking at what we're going to be doing in this class, which is just a very basic conceptual groundwork that everybody who is in this class is more than capable of with whatever math you've taken previously. This is more conceptual than mathematical. So the electronic energy levels of a hydrogen atom, also everyone in this class could certainly take Physics 3 if they wanted to. You're all more than capable of that as well. Okay, so for the hydrogen atom, E sub n is equal to K plus U electric, which is minus 13.6 eV over n squared, where n is equal to 1, 2, 3, etc. Notice these are integers. You never have 1.2, 5.6. It's always a whole integer number and always positive. All right, so this has been verified extensively through experimental results. This is more than just a theory at this point. So I need to tell you a little bit about the naming structure for ground states and excited states. So once again, let's go back to our energy diagram. So the ground state is the lowest energy level. And it is the n equals 1 state. The second energy level, E2, is the first excited state. So if an electron is in ground, it's not excited. If it is in equals 2, then it must have gotten excited to get there. And so that's n equals 2. And then it would follow for the third state, that would be the second excited state, which is n equals 3, and so on and so forth. So make sure that you're reading your problems very carefully to make sure that if you see something like the third excited state, that would be the n equals 4 energy level. And then of course for the hydrogen atom, that would be minus 13.6 would be ground. Okay, so You might be asking, how exactly do these electrons get excited? So, how do electrons get excited? Two main ways. Absorbing photons. So those are those light particles we talked about, and particle collision. And we will go through both and how they happen. Okay, so let's start off with photon absorption. So, atoms can gain energy from a photon only under specific circumstances. And it has to be very specific. We're in quantum land now. Namely, the photon needs to have exactly the right amount of energy. It's all or nothing. Nothing can be left over. It's going to take it all or it's going to take none of it. Okay, so what this looks like is you'd have your hydrogen atom plus your photon. So this is a gamma. This is the symbol for a photon. And this, if you put them together, and this is exactly the right amount of energy, then you get an H star, which is an excited hydrogen. So excited hydrogen. And so using the energy principle, you would write that as the final energy state, which is the excited hydrogen, which is the combination of the original amount of energy from the hydrogen plus the photon that it has now eaten. So you have the energy initial of the hydrogen plus the kinetic energy of the now newly absorbed photon. Okay, so let's do an example. And we'll see how to do this. All right, so a hydrogen atom is in its first excited state, which of course we know corresponds to the n equals 2 energy level. It absorbs a photon, raising the energy to the third excited state, which would of course be the n equals 4 energy level. What was that perfect energy of the photon? Because only the perfect amount of energy can cause this. So let's choose an easy system. That would be all particles. All the particles are going to come to play. And we're going to put them all in the system so that we can have nothing in our surroundings to account for. Okay, so building on that, we're going to start off with the energy principle. So the energy final is going to be equal to the initial energy plus the kinetic energy of the incoming photon. So the energy final, we have minus 13.6. And if we go back to the problem, we can see that it ended in the third excited state, which is the n equals 4 energy level. So this is going to be over 4 squared is equal to minus 13.6. And we said it started in the first excited state, so that's 2 squared, plus the unknown kinetic energy of the photon, plug and chug, minus 0.85 eV is equal to minus 13.4 eV plus kinetic energy of the photon. Add 13.4 to each side. And the kinetic energy of the photon, which was exactly the right amount, is 2.55 eV. All right, pretty simple, eh? All right, so you might be asking, what is the minimum energy required to raise a hydrogen out of ground? So unlike our previous problem where we were starting out with an already excited hydrogen atom and we were just making it more excited, we're going to start with hydrogen in ground. So then we'd be ending the lowest excited state is n equals 2, so we'd have 13.6 EV over 2 squared is equal to minus 13.6 EV over 1 squared plus the kinetic energy of the perfect photon, and that energy is 10.2 EV. Lower than that, hydrogen stays unexcited. It will not take a 9 EV photon and be in between. It is exactly the amount it needs, or it's not good enough. Okay, so that is excitation via photon absorption. Let's move on to collisional excitation. So if a fast-moving particle collides with an atom, some of the kinetic energy can be converted into exciting the atom. And any remaining K will be kept by the original particle. So in this case, you don't have to have exactly the right amount of kinetic energy. You just need to have either exactly enough or more than enough. And it is allowed to keep leftover kinetic energy. So, which is pretty useful. All right, so let's look at an example of collisional excitement so we can see how this works. So once again, the atom will take exactly the right amount that it needs. It won't take anything more, and it won't accept anything less. So in this case, we're going to look at exciting mercury. So we have an electron with kinetic energy of 6 eV collides with a mercury atom in ground. So it excites it to n equals 2, which for mercury is 4.9 eV above ground. So we know that this atom has taken 4.9 eV of energy from that electron. So it excites it. The electron deposits 4.9 eV of kinetic energy into the HD atom and goes on its way with a kinetic energy of 1.1 eV left over. So there you go. That's how that works. It started off with 6 keV. It deposits exactly 4.9 eV, and then it has 1.1 eV left over. So it would be going slower than when it originally excited. Now you might ask, what about that mercury atom? What's going to happen to that? So atoms do not like to stay in excited states. So eventually the mercury atom will de-excite by emitting a 4.9 eV photon. That's right, atoms are light producers. And to prevent de-excitation, then you could have a constant stream of exciting electrons move through HD, and then that you could keep it in its excited state. But once you stopped exciting it, it would de-excite through emission.